Okay, in this lecture we're going to cover the first part of our section 12.3 material on optimization. Now optimization is a term which is referring to finding the largest or smallest values of a function, which is one of the biggest applications that we'll consider in this course. How to maximize a function or minimize a function, and this has applications in several different disciplines. In particular for business or economics, we might be interested in maximizing profit, minimizing cost, maximizing output, minimizing effort, things like this. So let's start by introducing a little bit of terminology. So let's suppose that f is some function which has a domain capital D, which contains the number c. So in other words, the domain of our function is D, and our function is defined at c. So we would say that the function f has an absolute maximum at c if f of c is greater than or equal to f of x for all values x in the domain of the function. So that is, if the largest value of the function over the entire domain is at x equals c, then we say the function f has an absolute maximum at c. And the value of the function f of c is called the absolute maximum value of the function f on the domain D. So the actual value of the function at that point is called the absolute maximum value. Now similarly, we can define the absolute minimum of a function. So we would say a function f has an absolute minimum at c if f of c is less than or equal to f of x for all x in the domain of the function. So that is, if the function takes its smallest value over the entire domain at c, the function has an absolute minimum at c, and the value of the function at c, that is f of c, is called the absolute minimum value of the function f on the domain D. Now we would say that the function f has an absolute extremum at c if it has either an absolute maximum or a minimum at that point. And we would refer to the absolute maximum and minimum values of the function as the absolute extrema of that function on the domain. So to illustrate an absolute maximum or minimum and see how those values may differ from local maximum or minimum values, let's consider the graph shown below. So this is the same graph that we were looking at earlier in chapter 12 when we talked about local extrema. And we mentioned that at x equals 1, if we were to look at just values of x in a small interval around 1, it looks like the largest value of our function within that interval occurs at 1. So we would say that this point, or we would say our function has a local maximum at x equals 1, and the corresponding value would be our local maximum value of the function. Now similarly at 0, if we consider a small interval around 0, we see that our function appears to have its smallest value in that interval at 0. So we would say that this function has a local minimum at x equals 0, and the y value, which is also 0, would be the local minimum value. Now for this graph, we can also see, if we were to consider a small interval around 3, our function appears to have its smallest value within that interval at x equals 3. So we would say our function has a local minimum at that point. But if we think about this function being defined on the domain -1 to 4, we can see that this point is actually the smallest value that our function takes over the entire domain where we're looking at our graph. So this smallest value would be the absolute minimum value which occurs at x equals 3. Now, if we're restricting ourselves just to this interval -1 to 4, it looks like our left endpoint appears to be the largest value of the function over this domain. So we would say that we have an absolute maximum at that left endpoint at -1. And the corresponding y value, whatever it is, would be our absolute maximum value. So here a little illustration of absolute versus local extrema and what exactly they're representing. So let's look at an example. We've just seen from this illustration that if we have the graph of a function over some domain, we can pretty quickly identify its absolute extrema. So here we're asked to find the absolute extrema of the function who's graphed on the given interval. So for our figure in the left-hand plot, we're looking at the graph over the domain from -1 to +1. And it appears that the largest value of our function over that domain is occurring at this right endpoint. So here, our absolute maximum occurs at x equals 1, and it appears that the absolute maximum value is also 1. And the smallest value of our function over this domain is occurring at -1, and the corresponding minimum value appears to be -1 as well. So we would have an absolute minimum at x equals -1, where the minimum value would also be -1. So in our right-hand figure, we can see that the smallest value of our function over this interval from -1 to 1 appears to be at x equals 0. So here we have an absolute minimum occurring at x equals 0, and it looks like the absolute minimum value is also 0. And then our absolute maximum appears to occur at either of these endpoints of our domain, at +1 or -1. The corresponding absolute maximum value appears to be 1. So here we would have an absolute maximum at x equals positive or -1, and the absolute maximum value would be 1. All right. So here we can see if we have the graph of the function provided over some domain, it's pretty easy to see where its absolute extrema occur. So if we don't have the graph of a function, then how do we determine the absolute extrema of a function? Or more importantly, how do we know whether a function even has absolute extrema before we would try to find them? So those questions are answered by a result known as the extreme value theorem, which says if we have a function f, which is continuous on some closed interval from a to b, so including the endpoints, then f has both an absolute maximum and an absolute minimum on that closed interval from a to b. Moreover, each of these values occurs either at an endpoint or the interval of the interval, or at a critical number. So when we're looking for the absolute extrema of a function, we know as long as our function's continuous over a closed interval, it does have absolute extrema, both a maximum and a minimum. And those values occur either at the critical values of our function or at the endpoints of that interval. So let's look at an example making use of the extreme value theorem and see how we can find the absolute extrema. So here we are told to find the location of the absolute extrema of each function over the given interval. And in part A, we have f of x, which is some polynomial, so it is continuous everywhere. And we're looking at it defined on a closed interval from -2 to 0. So the extreme value theorem says it will have both an absolute maximum and minimum value. Now we know that those values must occur either at the endpoints, so at -2 or 0, or at a critical value of our function. So let's see if we can find the critical values of this function. Recall the critical values are values of x for which the derivative is undefined or 0. So here our derivative is 6x squared minus 6x minus 12, which is defined everywhere. So the only critical values would occur if this derivative is 0. So to solve for x, we could divide through everything by 6, and we have x squared minus x minus 2 is 0, which factors as x plus 1 times x minus 2 is 0. So we have critical values of -1 and +2. Now, one thing to be a little careful of when you're working with these problems is our critical values may not lie within the interval of interest. So in this problem, the interval that we're considering is from -2 to 0. So notice that this second critical value, 2, does not lie within that interval. So we'll make a little note here. This is outside of the interval. So we're not going to consider that value at all. Now our other critical value, -1, does lie within that interval. In fact, it's the midpoint of that interval. So to determine our absolute extrema, well, we know they have to occur either at the critical values or the endpoints. So we're going to look at the value of our function f at the endpoints. Those were -2 and 0, as well as the value of our function at the critical values that we found, which lied within our interval, in this case only -1. So substituting these x values back into the original function, f of x, let's see what we have. So substituting -2, we have a value of 0. When we substitute -1 into the equation, we have a value of 11. And when we substitute 0 into the equation, we have a value of 4. So now we look at what the largest and smallest of these values would be. We see that the largest value is 11. So this would be the absolute maximum value of our function. And the smallest of these values is 0. So this would be the absolute minimum of our function. So here the absolute minimum occurs at the left endpoint, x equals -2, and the absolute minimum value is 0. The absolute maximum occurs at -1, which was a critical value, and the absolute maximum value is 11. Now in part B, we have f of x is a rational function, quotient of two polynomials, on the closed interval from 0 to 3. And we see that for this function, our denominator, x squared plus 1, can never equal to 0. So this function is continuous everywhere. So since it's continuous over a closed interval, the extreme value theorem says it must have both an absolute maximum and minimum value on that interval. And those values occur either at the endpoints, 0 and 3, or at a critical value. So we need to find the critical values of this function. So we'll start by finding our derivative, f prime of x, using the quotient rule. So the quotient rule says we first take the derivative of our numerator, so negative 2, times the denominator, x squared plus 1. Then we subtract the numerator, which was negative 2x, and multiply by the derivative of the denominator, which is 2x. And the entire expression is then divided by the denominator, x squared plus 1, quantity squared. So simplifying a little bit, in our numerator, when we were subtracting the negative 2x, that's the same as adding a 2x there. So expanding, we have a 4x squared minus 2x squared, leaves us 2x squared, and then minus 2, all over x squared plus 1 quantity squared. So this function is defined everywhere, since our denominator can never be 0. So the only critical values we have are values which would make this derivative equal to 0. And as we've mentioned in our earlier sections, the only way that a quotient can equal 0 is if our numerator is 0. Or we can think about multiplying both sides by our denominator. And we have 2x squared minus 2 is 0. So x squared minus 1 is 0, and x would have to be plus or minus 1. But again, we have to refer back to our interval, which was only from 0 to 3. So we only care about the positive 1 value, since we're only looking at values of x within the indicated interval. So now, to determine our absolute extrema of the function over this interval, we're going to evaluate our function at the endpoints, which were 0 and 3, as well as at any critical values within our interval. And here the only one that was within the interval was 1. So we might make a little note that x equals negative 1 is not in the interval from 0 to 3. So we're only considering that positive 1 value. So let's see what we get. If we substitute 0 into our original function, f of x, we have 0 divided by 1, which is 0. Substituting 3 in for x, we have negative 6 over 10, or negative 3/5. And if we substitute 1 in for x, we have negative 2 divided by positive 2, which would be negative 1. So comparing these values, well, the smallest value would be this negative 1. So this is our absolute minimum. And the largest value was 0, which would be our absolute maximum. So this example illustrating how the extreme value theorem works. We know if our function is continuous over a closed interval, it will have an absolute maximum and minimum value. And to find them, we look at the value of our function at the endpoints of the interval, as well as at any critical values which lie within that interval. Now, sort of an extension of that concept, we can mention it is sometimes possible to identify an absolute extrema on an interval which is not closed by making use of the following theorem. So this theorem is known as the critical point theorem, which says if we have a function f which is continuous on an interval, call it capital I, and that function f has exactly one critical value within the interval I, let's call that critical value c, then there's two parts to this theorem. If f has a local maximum at c, then that local maximum must be the absolute maximum on that interval, if that was the only critical value within that interval. And if f has a local minimum at x equals c, then that local minimum would have to be the absolute minimum over that interval, as long as that was the only critical point within that interval. So let's look at an example making use of this critical point theorem. So we're asked here, if possible, find the location of an absolute extremum of each function over the given interval. So in part A, we have f of x is this polynomial on a now open interval from 0 to infinity. So to use the critical point theorem, we're going to start by looking for critical values of our function within that interval. And to find critical values of a function, we would look at the derivative of our function, which is 3x squared minus 4x minus 4, which is defined everywhere. So our only critical values or points or values of x that would make this derivative 0. And we can solve for x here by factoring. This factors as 3x. Here we have a minus 2, and here a plus 2. So 3x plus 2 and x minus 2 would equal to 0. So x could equal to negative 2/3 or 2. And as with our previous examples, well, we have to refer back to our interval. Here we're only looking at positive numbers, so this one critical value, negative 2/3, we will not consider. It does not lie within our interval. So within this interval from 0 to infinity, there is only one critical value, namely x equals 2. So if we can show that we have a local extremum at that value, it must be an absolute extremum within that interval. So to determine whether we have a local extremum, we could make use of the first derivative test. So here we're considering the interval from 0 to infinity, and we had a critical value of 2. So to determine the sign of the derivative to the left of 2, we could choose x equal to 1. And if we substitute 1 in for our derivative, we would have 3 minus 8, which is negative. So our function would be decreasing on that interval. And then to the right of 2, we could take x equal to 3, which would give us a positive value for f prime, and our function is increasing. So since we change from decreasing to increasing at x equals 2, that means we have a local minimum at x equals 2. But the critical point theorem says, well, if we only have one critical value in that interval, in this case 2, and we have a local minimum there, it must also be an absolute minimum over that interval. So here we could say we have an absolute minimum at x equals 2. And if we're interested in finding the absolute minimum value, we could plug 2 back into our original function, and we would have a value of negative 7. And there is no absolute maximum for this function on that interval. As x continues to get larger and larger, this function will increase without bound. There is no largest value. Now in part B, we have the function f of x is 2x times e to the 3 minus x on the interval from negative infinity to positive infinity, so the entire real line. So we want to locate any absolute extrema if possible. So let's start by looking for critical values. So here, to find our derivative, Well, we see f of x involves a product of two functions, 2x and e to the 3 minus x, so we're going to have to use the product rule. And we will also have to make use of the chain rule to differentiate this second factor, e raised to some function of x. So the product rule says we first differentiate our first function, 2x, which would have a derivative of 2, and then we multiply by the second function, left alone, e to the 3 minus x. Then we add the first function, which was 2x, times the derivative of the second function. So the derivative of e raised to some function would be e raised to the same function, but then we have to multiply by the derivative of this inner function. So the derivative of 3 minus x is negative 1. Now, if I look at my expression for f prime, I notice that both terms in this sum have a common factor of 2 times e to the 3 minus x. So to simplify, if I factor out a 2 times e to the 3 minus x, I'm left with 1. And then from the second factor, I still have an x times a negative 1, or negative x. And I see that this function is defined everywhere. So the only critical values I would have are values for which this derivative is 0. Now I know that the exponential function is always positive valued. It can never be equal to 0. So the only option I have is for 1 minus x to be 0, or for x to equal 1. So let's consider whether we have a local maximum or minimum at this single critical value. And the critical point theorem says, well, if it's a local extremum and that's the only critical value on our interval, it would have to be an absolute extremum. So looking at the domain of our function, in this case, negative infinity to infinity, we had a critical value at 1. And to determine the sign of the first derivative, or whether our function is increasing or decreasing on each of these subintervals, we choose a test value of x. So to the left of 1, we could choose a value of x equals 0, and substituting into this simplified expression for our derivative, well, we already said this 2 times e to the 3x is always positive, so we really only care about the sign of 1 minus x. So if x is 0, we have a positive value, so our function would be increasing, and then choosing a value of x to the right of 1, say x equals to 2, our derivative would be negative, so our function is decreasing. So the first derivative test says if we move from increasing to decreasing at that critical value, we have a local maximum at that value. But then since this was the only critical value within that interval, the critical point theorem says that it must be an absolute maximum. So here we have an absolute maximum at x equals 1. And to find the absolute maximum value, we would evaluate our original function at 1, which would give us a value of 2e squared.